Hello, welcome to the Chapter 27 homework preview. This time I'm going to go through the questions that you can see before you on the screen, namely Chapter 27, number 6, 10, 18. That's going to be part 1, this video you're watching right now. And then in a follow-up, I'm going to go through 50, 58, and 71. There are a couple of questions from Chapter 28 still in this homework set, namely ones related to the internal resistance of batteries. So if you're tackling those and you want a textbook for help, just be aware that you're going to find the answers to those questions at chapter 28, and they're the first few on the homework set if you do them in order. Alright, let's get started on the questions that I've selected to go through here. Number 6. And as usual, I want to go through the textbook version of them. The Mastering Physics version is going to be very similar, though it might be slightly differently structured in terms of how it's split into parts A, B, C, and so on. But that's good, right? Because it means you actually have to do a little bit of work and fill in the details and apply your new understanding. So 6a asks us, how many conduction electrons are there in a 1.0 millimeter diameter gold wire that is 10 centimeters long? Let me just start a new page here. For a 10 centimeter long wire, let me just draw it like this. Here's my front end of the wire. It has diameter, which is just circular. Most wires are. In fact, unless you're told otherwise, you can safely assume that it's a circular wire, a wire with a circular cross-section. So how many electrons does this contain? Now, how many conduction electrons, right? So conduction electrons means we're only counting those electrons that are free to go around, not the ones that sit in stable shells around their atoms. So the total number of electrons in here, number of conduction electrons, free electrons. And one way we can express this, it's going to be useful, is we're going to take the volume of the cylinder and we're going to multiply this by the number of electrons per volume, right? So take this times the conduction electrons per unit volume, right? So if my volume were 2 cubic meters, of course it is not, it is a thin wire, right? It's way smaller, but let's imagine it's 2 cubic meters. I'm going to take 2 times the number of electrons per cubic meter. So this quantity here is essentially a sort of conduction electron density, or the free electron density. The density of free electrons. And this is what this is. And this is a number, you just look up for different materials. This is Ne, that quantity, if you remember that from the video I made, for example. That is something you go and look up. And for gold, let's check, I wrote it down somewhere. For gold, it is, for gold, it turns out to be 5.9 times 10 to the 28. So it's a huge number, right? I mean, but you expect the electrons are utterly tiny. 10 to the 28. So you can look that up. Now, what's the volume of the cylinder? Well, you can figure that out, right? But it's going to be the front area times the length. So cross-section times length. Cross-section area multiplied by the length. What's the cross-section area? Well, the cross-section area, it's a circle, right? It's going to be pi r squared. The only thing you could be careful about is that r is the radius, right? But we are given d, which is 1 millimeter. Of course, the other thing is you have to make sure you convert to meters beforehand, because this is given in number per meter cubed. Alright, that's it. You can figure it out from there, right? Just fill in the numbers, work it out, you're going to get the total number of electrons. Part B is very similar. So part B is asking us about the sea of electrons. And this is kind of idea that the electrons, they're sort of drifting sideways. I kind of have this driftwood image in my mind, or some pieces of wood drifting down a river. Of course, realistically, right, the electrons are whizzing around and just sort of tend to move, on average, more one way than the other. So it's going to be 6b. So it's asking us how far the sea of electrons must move in order to deliver minus 32 nanocoulombs to some kind of electrode. The way you might visualize this is, here's my wire, right? Let's put it from the side. And here's my electrode. Maybe it's a sort of plate of like a parallel plate capacitor or something like that. Doesn't matter. It's my electrode. The question is, how many, what kind of amount of electrons, they're all over the wire, but I'm asking how many of them, they're all drifting right, have to enter the electrode so that they add up to minus 32 nanocoulombs. And your numbers might be different, of course, in your mastering physics version of the question. So I'm going to write down to minus 32 nanocoulombs total enter the electrode. Well, the first thing you can figure out fairly easily, right, is how many electrons correspond to 32 nanocoulombs. It's one of the first sort of problems you tackled in this course, figuring that kind of thing out. But let me just go straight to the question here. So again, this is kind of the cross-section area, right? And this volume here is gonna enter the electrode. So we're kind of back to pretty much the part A, except the other way around, right? The volume of this thing is going to be pi r squared times the length, right? That's the distance of drift. We don't know what it is. So then it will be a question mark here. It's my variable, the question mark. Volume pi r squared times what? Such that the volume times the number of electrons per volume times the charge per electron is equal to minus 32 nanocoulombs. Of course, if you first use this to calculate the number of electrons, you'll just multiply those two, right? Because you've already taken care of this by essentially dividing this by E. I'm going to do it this way. So we're multiplying the volume by the number of electrons, free electrons only, of course, per volume. That gives me the total number of electrons. Then I'm going to multiply this by the charge per electron. That's just a fixed value. I guess, okay, I should be a bit more careful here. And the electron charge is minus E, right? Confusingly, just E is 1.6 times 10 to the minus 19, which is a proton charge. Electron has a charge minus E, and I'm going to need that because it's for the minus sign over here. Of course, remember also that this is in nanocoulombs, so nano 10 to the minus 9. So use that, and you can solve for the unknown, right? Because the volume this term here is just what you got up here. Hope this makes sense to you, right? This box of electrons, kind of volume, gets squeezed in, kind of like the tip of a toothpaste, right? You squeeze in the back. In this case, there are more electrons pushing it along, and they squeeze into the electrode. Alright, that is number 6 for you. You can fill in the missing pieces. Let's now go to number 10. So number 10. So number 10 actually involves a concept that we haven't really talked about yet, that you might have actually wondered about if you've gone to the store recently and tried to buy a light bulb, right? 10 tells me that the current in a 100-watt light bulb is 0.85 amps. So a 100-watt light bulb. Now you're confused, right? You thought you knew what you were buying when you went to the store, and I've got a 100-watt light bulb. But now you're like, wait a minute. Doesn't the power output, this is clearly a power output, 100 watts, but you say, doesn't the power output of a light bulb depend on the voltage across it? Of course it does, right? So how can a light bulb decide to put out 100 watts if it can't control the voltage across it? So it's kind of 100 volts, right? 100 watts. You ask at what potential difference? At what voltage? What is this nonsense? At a store on the package it's 100 watts, but I mean you could connect it to a 6-volt battery and try that. You're not going to get 100 watts. So what we mean by 100 watts, 100-watt light bulb, is what it implies is the power output is 100 watts when delta V is 120 watts. Now this, it doesn't tell you that when it says 100-watt light bulb. I mean, maybe in the small print somewhere it says connect to 120 volts. That is the voltage that you get essentially from the two ends of a wall socket. The potential difference, in your main sort of house domestic circuitry is 120 volts. So what it's telling us is that at 120 volts potential difference, we're going to get 100 watt. You can actually check that 120 times 0.85 is really close to 100. Not exact, but it's extremely close, right? So really they're cheating you. They're telling you it's 100 watts, but it's not 100 watts unless you plug it into 120 volts. What would be the more physical thing to do, like if you put a physicist in charge of designing the advertising on a packet, it would tell you the resistance of the light bulb. And the higher the wattage, right, the lower the resistance. So the smaller numbers would be better. Of course, that probably wouldn't sell. Also, I guess people at this point have more of an understanding of 100 is more than 60, therefore it's brighter than worrying about the resistance and calculating currents. But that's just an aside, really, right? You're told this is the current in the particular situation that we're looking at. And we're told that the filament inside the bulb is 0.25 millimeter in diameter. Let me show you. So if you look at a light bulb, right, you look inside, there's a wire, it sort of curls around like this, and that's this. This is super thin, is the filament. It's here, right? It's a very thin, long wire. And because it's very thin, very long, it has a high resistance. We're going to get the majority of the potential difference of the circuit that's hooked up to is going to be between here and here. So the power output of essentially of most of the circuit is going to be through this part here. What does the power output do? It heats up the metal. And it heats it up by having the electrons essentially bump into the atoms, right? Remember, inside the wire, and so you're going to start to jiggle more because they get energy from the electrons as the electrons get accelerated because of the electric field inside the wire. So this gets hot. Now, when metal gets hot, it starts to glow, right? Now, normally, you turn on your stove, if it's one of those metal ones, and it starts going red, right? This one glows, say, white or yellowish. What it tells you is that actually this filament is extremely, unthinkably hot. It's, several thousand degrees Celsius hot. Those are several thousand degrees Fahrenheit, if you're wondering. So, you make those out of materials, something like tungsten, which has a very high melting point, so it doesn't melt. If you made a little iron wire like this, it would just melt. It's dead. The light bulb stops working. But it glows so bright because it has this super high temperature. And when you get energy efficient light bulbs, what they try to do is you try to minimize you try to set it up in such a way that you get the highest possible amount of light for the least amount of heating up. So less energy is actually spent producing the same amount of light. Inherently, the light comes from the thing being super hot. Alright, now we've covered the conceptual idea. This wire here, right, we zoom in, of course it's a wire, right, it can pretend it's straight, and just zoom in a tiny bit of it. And what we're told is, we're asked about the current density. We're told the diameter, and we're told the diameter D is 0.25 millimeters, so that implies the radius is half of that, or 0.000125 meters. It's half of this, and I convert it to meters. So we've got the current, we've got the radius, and therefore the cross-section, right? Cross-section of this. So I can ask, well, how much current do I get per area? That's my current density. And that's current per cross-section area. You can figure out a cross-section area because it's a circle and you know the radius. Right? I'm not going to do this for you. And you know the current because it's given to you. So the rest is just plugging in numbers. You can finish that part off. That was only part A. What's part B? In part B, we asked what is the electron current in the filament. Now, electron current is just the number of electrons. So this is really more like a conversion almost. We have, for 10B, right, we have I, in my case it's 0.85 amps. So an amp, of course, is a coulomb per second. So I'm going to get the electron current, the number of electrons, by having the current, dividing it by the electron charge. Because, right, the current itself, charge per second, is number of electrons per second times electron charge. So if I go the other way, I just divide I by the electron charge, get the electron current. Super easy here. Not very much to do, just to understand the concepts. Alright, that's 18 done. You can fill out the missing details. There actually isn't very much left for you to do. The next one is number 18. 18 is just the following. So 18, since we have a square wire this time, right? So read the shape, please. Square wire. Draw it like this. Looks more like a sort of metal beam, but you can imagine it's just, very long. And we don't know how long it is. It's something crucial to understand here, right? We know the area here because we know it's, in my case, it's 2 millimeters by 2 millimeters. Right, so I can figure out what is the cross-section area A because it's a square. So I know A is 2 millimeters by 2 millimeters. So we've got this, right? You can figure out what that is. Remember to convert to meters squared though, because we're going to need it later. So we know the electric field in the wire in volts per meter. Trying to find the current. Now, if you're confused, electric field, how does this relate? One little trick we can do is you want to find a current. Okay, I'm just going to write E is delta V over R, right? Ohm's law. But R is rho, the resistivity. And that's a property, remember, that depends on sort of the physical properties of the material, like how close are the atoms together, and determining how often electrons bash into the atoms, how many free electrons there are, and so on. So it's this times the length. Like the longer it is, the more resistance, the further the electrons have to travel through that maze of atoms, or through that sort of bumpy, it's like bumpy river, right? They're flowing down a river, but there's constant rocks in the way that have to like go around and they get pushed back and so on. Another actually good analogy is the resistance. Another good analogy for the electrons in a wire, by the way, is a pinball machine. Right? Remember a pinball machine? You look at a pinball machine, and it's sort of from the side. It looks something like this. Like there's the button, right? It's a classical old pinball machine. You shoot the ball up, and then if you look at it from the top, right, it looks like this. And there are all these things that sort of make it bounce around. All these little sort of bells and whistles and springs and whatnot. And the ball's going to bounce around everywhere. But as time goes by, eventually it's going to make it down the hill, and unless you shoot it back up, it's going to bounce around and come back down because of the slope. It's a bit like the electric field, pushing it down the hill, but on the way it might do a lot of bouncing before it reaches the bottom of the hill. Right, so in this analogy, pinball machine. This is my artistic drawing of the pinball machine. That's a good analogy for the electrons to in a wire, electric field being analogous to the downhill slope here. Alright, let's come back to the actual questions. So the current is this, the resistance is this, so I can write the current as delta V divided by rho times L and multiply by A, right, 1 over R. Okay. Now, I know A, let's take some stock. I know this one. The resistivity, do I know this? Actually, I do, because we're told it's aluminum. So we can look it up. Aluminum, or aluminium, as you call it, in other English-speaking countries. This is aluminum, and you can just look up what is the resistivity of aluminum. I can do it for you. It is 2.8 times 10 to the minus 8 ohm meters. And that's on page 753 in the textbook, if you have the 4th edition. So that's something you know. In an exam, say, of course, you'd be told what the resistivity of, say, aluminum is. So, but we don't know the length of the wire, and we don't know delta V. So are we stuck? Of course we're not, because what we do know is the electric field. Right? An electric field is potential difference per distance, per length. So this thing here, that's just E. Right? That's why this question is a bit harder, because you have to recognize this. That normally we put delta V is one thing we decide by battery, like what battery are we hooking our wire up to, and the length of the wire is kind of a given. Here's a 2-meter long wire. But in this case, we don't know how long the wire is, but we know the potential difference per length. That's the electric field. Because the electric field is the slope, the downhill slope of the potential. The potential, how much is the potential change per displacement. This is electric field, which we know. So that means we can work out the current without any further problem. Alright, that's it. That was the first part. In the second part, I'm going to go through questions 50, 58, and 71. I will see you there.